Hello everyone, my name is Cameron Hicks, and today we are going over Lab 4, which is oscillations in simple harmonic motion. In this lab, we analyze the oscillatory motion of a spring mass system moving in two dimensions. The goal was to use video analysis software tracker to extract X and Y position data of the moving mass and then build a computational model in GrowScript that simulates the same motion. By comparing the observed and simulated results, we could assess how well our physics-based model reflects real-world behavior. Finally, we examined energy conservation and calculated oscillation periods from both directions to deepen our understanding of the system's dynamics. The foundation of this model lies in Newton's second law and the energy principle. We consider the forces acting on the mass, gravity, and the restoring spring force, which together produce oscillatory motion in both x and y. For each time step, the program calculates net force, updates velocity and position, and records the resulting energy changes. If the total energy remains roughly constant, that supports the idea that energy is conserved in the system. So for a system in initial conditions, the observed system was a small mass and its spring, and the surroundings was the backdrop wall, unobstructed path, and stationary camera. And then the initial conditions was the mass was 0.4 kilograms, spring constant 6.3 newtons per meter, and then relaxed spring length was 0.123 meters. Initial position negative 0.113 meters, negative 0.042 meters. Initial velocity 0. And also from tracker, we observed that at 0.079 seconds, the X position was shifted about 1.13 meters, while at 1.6 seconds, it has shifted to negative 0.7 meters, which is consistent with one half the oscillation. And for observational data, using tracker, we plotted X and Y positions versus time. Both graphs showed smooth periodic motion typical of a spring system, though not perfectly circular. The oscillations had slightly different amplitudes and phases in each direction. This suggested the system might have been swinging diagonally or that damping and tracking inaccuracies affected the symmetry. This is a video reflecting that. And as you can see, the origin I had was roughly the equilibrium position. For the computational model, in GlowScript, the motion was modeled using the same physical parameters, spring constant, mass, and gravitational acceleration. The code used step-by-step updates to compute position, velocity, and energy at each time frame. When plotted, the X and Y position curves closely match the tracker data, with some deviations due to measurement noise or parameter rounding. The energy graphs showed small oscillations in kinetic and potential energies, but there's some. This orange line of total energy remained mostly constant, which demonstrates conservation of energy. For observations versus model, the simulated trajectory matched the shape and period of the observed path pretty closely. The computational model captured both the X and Y oscillations with realistic phase shifts, given a near elliptical motion just like the experiment. This confirmed that the physical assumptions and numerical methods used in the model accurately describe the motion recorded. Some possible errors was that in tracker, small calibration errors, imperfect scaling, or parallax effects could shift position data. The frame rate and then data sampling might also cause timing inaccuracies. In the computational model, using a finite time step introduces small numerical running errors, and the model assumes no air resistance or internal friction, so lack of damping means total energy stayed constant, unlike in a real system. For discussion and additional questions, the additional question we included was, what if air resistance were included? And if that was the case, the object would experience a small but continuous deceleration, causing the model's model slope to decrease slightly over time. Then we also have the energy principle, in which the energy changes oscillates around zero, showing conservation is satisfied. And for the comparison of periods, for the X position, it was roughly 3.6 seconds. And for the Y position, it was 2.9 seconds. And a slight difference due to initial Y displacement and slight damping in real system. And also the origin in which we put our calibration affected that as well. And then just to reiterate, some possible errors was the video parallax, timing inaccuracies, calibration misalignment, and coding errors. Overall, this lab showed how tracker data and computational modeling complement each other, allowing us to visualize, simulate, and understand complex oscillatory motion in two dimensions. Thank you.